So very good afternoon to everyone. Welcome to today's live interactive session on geosynthetics and reinforced soil structures. So today we'll be discussing on the seventh week lectures. Yesterday also we had a live session, where we actually solved some problems regarding the design of reinforced earth wall using geogrid, right? And then we solved some basic problems regarding the design of slopes, right? Embankments, okay, reinforced embankments. And then later at the end we solved one problem where we designed one steep slope, okay, steep slope using the Jewels method, right? So that was what we did yesterday. And in the today's session also we will be beginning by solving one problem using the Jewels method. We'll be solving one problem with Jewels method first, and then after that we will be seeing how geocells are actually used to reinforce the foundation of a embankment. Okay, so say you have a soft soil layer, and above that you need to construct a say an embankment or something like that. So you obviously need to reinforce the foundation, right? So you have a soft soil layer. Obviously you cannot directly construct something over it, because as that soft soil layer is weak, there will be very high settlements, right? Very high settlement, it is going to fail nonetheless. So we will try to use geocell to reinforce that. And a problem was already discussed in the main lecture classes, but just we will be just going through that one a bit, because see, uh, the method which is used to solve the problem using geocell is a little bit advanced, right? It's a little bit advanced. The slip line method is used, and many things in that is actually not clear. So what we will be doing is that still we will be like just seeing, having a glimpse over it. Okay, we won't go much into the depth, but we will be go having a overall glimpse of the topic. All right. uh, yeah. So yeah. So as I was saying, yeah, so we will be doing, first we will be solving a problem from using the jewels method, and we will be solving the just not solving, actually just looking into that, what's actually happening during the solution of the geocell thing. Okay, when we use geocell to reinforce the foundation, what thing is actually going on there. So just you will be having a glimpse over that. And the content of this week is not that much, it's very less, so we will be having a lot of time towards the end. So what I will be doing is that I will be actually introducing some new topic to you, which is not, with some extra topic actually, some extra topic which is actually not a part of your syllabus, but still as we have some time, I thought that it's better we discuss something. So as just as a extra, what to say, as an extra knowledge, you can have that thing. Okay, so we'll discuss some extra topic towards the end, and with that we will end the class, we will sum up the class. All right. So let us begin today's session. So this is the problem that we have. We plan to construct a soil embankment at a 70-degree slope angle with the horizontal and 10-meter height. Okay, so we plan to construct an embankment. The slope angle of the embankment is given, that is 70 degrees with the horizontal. Obviously the angle is 70-degree with the horizontal. The height of the embankment is at 10 meters, and that is to be reinforced with the unidirectional geogrid with tensile strength, long-term design tensile strength of 25 kilonewton per meter. So the long-term design strength of the geogrid that we are to use is given, and that is 25 kilonewtons per meter. Okay. The soil is granular with unit weight 19 kilonewton per meter cube. The friction angle of the soil is 35 degrees and it has no pore pressure. So yesterday also we solved a problem of similar conditions where we did not consider pore pressure, so that is Ru is 0. So in today's problem also we will be taking Ru is 0. Uniform surcharge of 25 kPa is there at the top. Okay, so extra here what you are having is that there is a surcharge of 25 kPa which is there. Determine the number, spacing and length of the individual geogrid layers that we will be using to reinforce the soil. So in order to construct this steep sloped embankment, we need to use some reinforcement. We will be using geogrid reinforcement. So finally we had to actually determine how many number of layers of geogrid reinforcement you are using, the spacing of this reinforcement and the length of the individual geogrid layers. All these things we need to determine. All right. So let us start. So see, first what we will be doing is that we will be first we will be determining the equivalent height. So what is equivalent height? So the height is given, right? Height is 10 meter, but there is a surcharge. So if we want to replace the surcharge with with some height of the embankment, we can do that, right? So just by we can have an equivalent height. So that equivalent height will actually include the effect of the surcharge. So how do you do that? First let us find out the so height is 10 meter, it is the height of the embankment, and we have a surcharge of 25 kPa. That if we divide by 19, which is the unit weight, you will get the equivalent height. Means the 19 kPa surcharge we are substituting that by a height, some height of the embankment. Okay, right. Now what the next thing that we have to find, that is the force that is coming. Okay, the force that is the lateral pressure, the lateral force that is coming. For that we need the lateral earth pressure coefficient. K. Now from where can we calculate the K? So Jewel actually gave some charts from where we can calculate this. So first chart is already solved this similar kind of problem in yesterday's session also. So if this should be very clear to you actually. So see, the first chart gives the minimum force required. From here we can get the coefficient K. So let us see. So what is beta? In our case beta is 70 degrees, and then we have the phi value. The what is the phi value that is given to us? That is 35 degrees, right? So from here you can get that. So approximately you can take the K as, all right. Now see, now we got the K, so therefore we can find out the design lateral force. Right, so half into 19 into equivalent height square. So please calculate this one. Half into 19 into 11.32 square into 0.14. Please calculate this. come as 170.43. All right. Now next we need to find out the number of layers. So what will be the minimum number of layers that we have to give? There is some power shutdown. Okay, so if my system gets turned off, please give me some time so that I can like rejoin. Like the video might get turned off for some time. Okay. Yeah, so as I was saying, minimum number of layers. Just give me a minute, okay? Just give me a minute, huh? Yeah. So what is LTTS that is given in the question? That is 25. Approximately 7 layers. So approximately 7 layers of reinforcement we need to use. All right. So approximately 7 layers of reinforcement we need to use so that it takes care of the total force that is coming. All right. Now next is to find out the length of the reinforcement. How do you find out the length of the reinforcement? For that, see, we have two charts. This chart will satisfy the overall criteria, overall stability criteria, and this will be satisfying the direct sliding criteria. So you already discussed in what case what we have to use in the yesterday's session. So let us find out LR by H overall. So 70 degrees here. Yeah, something here we will get. So approximately say 0.41 L by H prime. Direct sliding you will get 0.22. So obviously we will be choosing this, therefore L is 0.41 times 11.32, 4.64 meters. All right. So this is what we got. Right. Now next what we have to do, next we have to design the how we are going to place the reinforcement. Okay, you are going to design how we are going to place the reinforcement. Okay, so minimum number of reinforcement that we have to give, that is 7 that we calculated. So obviously more than 7 number of layers of reinforcement we have to give for us for so that the total load is being taken care of. All right, so now let us see. So for that I will just stop sharing from here. I will share my screen from here actually. Yeah, so I hope it is visible. So first we will be having the depth, then vertical pressure, then permissible spacing, which is equal to TLTDS divided by Ka times vertical pressure meters. Okay. Then we have the spacing. Yeah. So let us provide. So we have total height is 10 meters, right? So depth, say, yeah, like this. Let us space, and then we have the vertical pressure. All right. So we have the vertical pressure. Vertical pressure is what? 19 times the height plus 25 kPa, which is our my surcharge. Okay, done. So we got this. Next, you have the permissible spacing. Permissible spacing is nothing but TLTDS, which we calculate, it is 25 divided by Ka. Ka is how much? 0.14 times the vertical pressure. Alright, so this is the vertical permissible spacing. So what we can do, if we want to see, what we can do is from here to here we can provide 0.75 meter spacing, right? And from here to here we can provide 1 meter spacing. Okay, so this is how we decide the spacing. Alright, so I will just copy this and paste in the PowerPoint so that it's a bit easier for you later. Stop sharing. Go here. I will again share from my iPad. Yeah. So this is what we decided. Okay, this is how we decided the everything. Okay, so we can have like this. Okay, so this is the slope, right? Slope, and this is 10 meters. So like this. So first layer we can provide a depth of 0.25 meters, and then at every 1 meter here we can provide, and in the below we can make the spacing as say 0.75. So like this we can provide. So see, so how many layers are we providing? So provide reinforcement at levels 0.25 meter, 5.25 meter, 6.25 meter, 7 meter, 7.75 meter, 8.5 meter, 9.25 meter, 10 meter. So how many layers are we providing? 1 2 3 4 5 6 7 8 9 10 11 12. So 12 layers. So we actually required 7 layers, but we have provided 12 layers greater than 7. Okay. All right, now what is the reinforcement length that we are providing? That is nothing but this 4.64 meter. Now obviously see this 4.64 meter we got from the chart, right? We got from the design chart. So obviously this is going to satisfy the sliding criteria, but still just as a check we will just recalculate it, just see if it's really satisfying the sliding criteria or not. Okay, now check for base sliding. So this is our lateral force that is acting. Now what is the resisting force? Is 0.8 times 1035. 0.8 is the coverage ratio. 0.35 into length times the height, equivalent height times 19, that is the unit weight, times 0.5, because we are averaging this. Okay, average your resisting force you are calculating meter. Therefore factor of safety is 270. Short, which is greater than 1.5, so safe. All right, so like this actually we have to do it. Okay, so just by using the what to say, the design charts, we actually calculated everything. Okay, we use the design charts to calculate the what to say, calculate your force that is coming, and then we calculate the length of the reinforcement, and then we find out the number of layers and all those things. Okay, spacing, everything we decided using the design charts only. So these design charts actually make our task a little bit easier. Okay, that's all. Okay, so next we will be starting this the designing with geocell. So just give me 2 minutes, then we will start. Yeah, so geocell for reinforcement of embankment based on soft soil. That means what? Say you have an embankment. Okay, you have an embankment. The base of the embankment actually, at this base of the embankment, wait, I'm not able to draw. So at the base of the embankment, we have a very soft soil. So in this case, when we have very soft soil, directly we cannot construct the embankment over it, right? Obviously, because the soil is weak, very soft, the embankment is going to settle down. All right. So what we do, we actually provide a layer of geocell. Provide a layer of geocell so that it prevents the lateral outward movement. See, so we have a embankment here. Here we have the very soft soil, and here we have the firm soil. Okay, here we have the firm soil, strong soil there. So what happens generally, there is a tendency that this there is a tendency, obviously, see, the soft soil is sandwiched, right? Sandwiched. Top we have the embankment, at the bottom we have the farm soil. The soft soil is sandwiched between them. So due to the load coming into the soft soil, obviously there is a tendency for lateral outward movement. And there is a tendency for lateral outward movement of the soil. So what happens, this geocell, when you provide, these geocells actually prevent the lateral outward movement by rotating the maximum principal stresses and the maximum shear stresses. Okay, it rotates the maximum principal stresses and the maximum shear stresses from this direction to this direction, and so it prevents the this sliding. It's trying to go away, like slide outwards, but the geocell actually prevents that outward movement. Okay, and how does it do that? So generally, see, if we don't have geocell, the failure surface, say, will be something like this here. But what happens when we use the geocell, the failure surface is pushed down. Okay, so the failure surface then passes through the farm soil. So actually this prevents the lateral outward movement. Okay, this is how the thing works actually. Okay, now the designing methodology, the designing using the geocell, many researchers have given many methods. Okay, so one of the most important method is that based on the slip line method that was given by Jenner, Bush and Bassett in 1988. So the title of the paper I have given here, the use of slip line fields to assess the improvement in bearing capacity of a soft ground given by a cellular foundation mattress, that means geocell, installed at the base of an embankment. Okay, so embankment, at the base of the embankment we are installing the geocell. Okay, so this was actually given by Jenner, Bush and Bassett, and this paper is actually the proceedings of the International Geotechnical Symposium, Theory and Practice of Earth Reinforcement, held at Walchema, Rotterdam, Netherlands, right? So it's like a conference, it's a conference paper, and it was given by Jenner and other co-authors. All right, so they actually showed that how the slip line method can be used to determine to assess the bearing capacity improvement using the geocells. Okay, now what is the slip line method? This slip line method is a little advanced topic. Okay, the slip line method is a little advanced topic. We study advanced geotechnical topic, you might not have studied that. So in slip line method, it's actually a plastic equilibrium concept. So generally whatever the theories we define, this bearing capacity theories and all, these are all limit equilibrium concept, right? Where the soil is in elastic state. So we consider that the soil is just in the verge of failure. So we equate the disturbing forces and the resisting forces. We consider that along a slip circle the failure is just about to occur, and in the slip circle there is some resisting forces that develop and there is some disturbing forces that develop. So these are limit equilibrium forces. But this slip line method is actually a plastic equilibrium concept. So we consider that the whole of the soil at that point, at all the points in the soil at that state is in state of plastic equilibrium. So what we do is we solve the different basic differential equations. We combine the basic differential equations which define the plastic equilibrium of the soil. We combine them with the mode circle, the failure theories, mode column failure or the failure envelopes to determine a set of curves known as the slip lines. Okay, the slip lines in simple word you can consider, in simple terms you can think of the slip lines. The slip lines are some family of curves. The slip lines are some family of curves which actually denote the probable line of failure. Probable line of failures. Okay, you can just in simple terms you can just think for now, for this moment you can just think it of something like that. So slip lines are a family of curves. You will see alpha and beta curves. These are family of curves that are some solutions. This, how do we obtain these curves? These curves we obtain, these curves are nothing but solutions of differential equations. Okay, solution of differential equation, and this solution actually gives us the family of curves, and this family of curves actually gives us the slip line. So this method is known as slip line method or method of test characteristics. So many allied methods are there, or many allied names are there of the same method. Okay, so we won't go much into the depth of it, but just we'll see what is being done. So it is written, so in this design the plastic bearing failure of the soil was assumed instead of slip circle failure. So as I said, the plastic failure, the soil is considered in the plastic state. Okay, instead of the slip circle failure. The slip circle failure is what? The slip circle failure is a limit equilibrium concept. Limit equilibrium concept means the soil is in the elastic state at the verge of failure. It is the verge of failure, but it is in the elastic state in the verge of failure, and there what we consider a slip circle where the failure is going to occur, and then along the slip circle we equate the resisting and the disturbing forces, right? So that is the limit equilibrium. But in this case the slip line method is a plastic equilibrium concept where the plastic bearing failure of the soil is assumed, right? This type of failure was expected for embankments whose width is more than 4 times the depth of the foundation. So this is the condition that has been enforced. This type of failure or this type of mechanism is only seen when the width of the embankment, the width, it is the width of the embankment is more than 4 times this depth of the soft soil layer. Okay, the foundation soil. So the width of the embankment should be more than 4 times this depth of the foundation soil, weak soft soil foundation. Okay, soft foundation soil. All right, the soft soil analogous to the block was assumed to get compressed between the geocell matrix at the top and the hard stratum at the bottom. So we have this soft soil here. So this soft soil is assumed to get compressed between the geocell layer which is at the top and the hard soil layer which is at the bottom. Okay, this analogy was used for developing non-symmetric slip line field in the soft foundation soil. So this analogy was actually derived from the metal plates. Okay, so soft metal plates sandwiched between some tough hard metal plates. So from that this analogy was drawn into this case soils where the weak foundation soil layer is compressed between a hard strata and the geocell layer. From there we drew this analogy, the researchers drew the analogy and developed this non-symmetric slip line field. Okay. Now, a 15-degree slip line field was used to determine the bearing resistance of the soil. The 15-degree slip line field means what? These lines, family of curves. So this slip line field, we'll see that later. We'll see that 15 at or 15-degree intervals. Okay, from here at 15-degree intervals, these lines are actually drawn. Okay, so that is what it is given here, and this 15 degree was actually suggested by the authors. Okay, the authors of this paper, Jenner et al. Okay, the construction of slip line field and corresponding bearing pressure diagram are discussed in detail by Jenner et al. 1998. So I recommend that you please go through this paper once. So in detail everything is, obviously they haven't discussed the slip line method in detail, but for studying the slip line method, you can go through some advanced soil mechanics or advanced computational geomechanics books. So this is a numerical technique. So slip line technique, slip line method is nothing but a numerical technique. Okay, so you can go through certain computational geomechanics books, there you will get what the slip line method is and how this slip line method is applied to this case. It is described very nicely in this paper by Jenner et al. 1998. So I suggest that you go through this paper by Jenner et al. 1988. Okay, so in this paper very clearly everything is given. Okay, how this slip line method is enforced in our scenario. All right. Now next we have the typical bearing capacity diagram for the geophysical supporting embankment for the slip line field shown below. So typically, see, so here we see embankment is there, and then we have the geocell layer. Now at the base of the geocell layer, we have to determine the pressure, the bearing pressure that gets developed. We need to determine the bearing pressure that gets developed. Okay. So initially at the leftmost extreme edge, it is assumed that the the bearing pressure that is developed is equal to that for the elastic limit of the soil, is equal to the elastic limit of the soil, that is nothing but 5.71 cu. Cu is the cohesion. Okay, so at the left end, it is assumed that the soil will have a bearing pressure that is from the elastic limit of the soil. So at this point, so this you can consider the y in this time, in this vertical direction we are plotting the bearing pressure. So at this point the bearing pressure is 5.71 c. Then it is considered that up to a d distance away from that point, d is nothing but the thickness of the layer, thickness of the this foundation weak foundation soil layer. Okay, so this d distance from the left side, from up to this d distance, we will continue, the pressure will be same, that is equal to the 5.71, right? So till this point we know what the bearing pressure is at the bottom. We know the bearing pressure. Now using the slip line method, what we need to do, we need to calculate the bearing pressure at all these points up to here using the slip line method. So till this point we know. From here, using the slip line method, we will see how we can determine the bearing pressures at all these points. Okay, at all these points we can determine the bearing pressures, okay, using the slip line method. Okay, so we will see a certain variation like this variation it's coming. Okay, here the value is this, so finally we get some value here. Okay, this at this point. Now it is said that at a distance of 1.25 d there is a constant decrease, and this remains same. So this is the line of symmetry. This is embankment. So at the center we are drawing this line. This is the line of symmetry, and from here to here we have a certain increase. This increase, and this remains constant up to a distance of 1.25 t. Right. So how to determine this increase? We will see that. Okay, expression is given by Jenner et al. Okay, so directly by using that expression we can actually, if we know the value here at this point, we can also get this value. Okay, at this value we can get that. So we will see that. Okay, the bearing capacity diagram was developed by working from the outer edge of the slipline field inwards to the boundary of the rigid head. So this is the boundary of the rigid head. Okay, so from here this side to this side, from the outer edge we are working towards this side to the boundary of the rigid head. So this portion is known as the rigid head. So why it is known as the rigid head, we will see that now. Inwards to the boundary of the rigid head, defined on the slip line field by the ratio of the geocell width to the depth of the subsoil layer. Okay, that is fine. A rigid head is the term used by Jenner 1988 to denote the soil zone which does not experience plastic strains. Understood? So that rigid head portion 1.25 d, length portion, that is considered as a rigid head. So why it is considered as a rigid head? It is considered a rigid head because it is assumed by general authors that that portion won't be experiencing any plastic strains. Okay, rigid, we have a rigid elastic types. Okay, so it will just behave as a rigid body and it won't experience plastic strains, and that portion is known as called as the rigid head. Alright. Thus, the slipline field is used to define the maximum allowable pressure distribution within a zone of limiting plasticity. Thus, the slipline field is used to define the maximum allowable pressure distribution within a zone of limiting plasticity. So finally, that is using the little we used to define all these pressures during the zone of limiting plasticity. So if you see, you can we can just think it in a way that in the leftmost side where we just this end, we have the soil having a bearing pressure of 5.71 cu, and then the bearing pressure is actually increasing. The bearing pressure is actually increasing. So you can think it of that way, that the capacity of the soil to take loads is increasing. Alright, the capacity of the soil to take load is increasing. Means initially, see the leftmost point, we have 5.71 cu. That is the elastic limit. That is the bearing pressure or the resisting pressure of the soil. But as we go rightwards, due to the action of the geocell, the bearing pressure or the capacity of the soil is increasing. That is the elastic limit is going high. That is the soil can take more amount of load before going into the plastic state. The soil can take more amount of load before going into the plastic state. Alright, so you can think it in this way. Alright. The tensile forces in the mattress are determined, that it is the tensile forces in the mattress means the tensile forces in the geocell mattress, the geocell layer are determined. The tensile forces in the geocell layer are determined from the stresses acting on the base of the mattress. Okay, from the base of the mattress. So we will determine the horizontal pressure that is coming at the base of the mattress. We have some expression we will see in the next slide. So from that expression of horizontal stresses that are coming at the base of the mattress, we are going to calculate what amount of strength of geocell we need to use. Okay. The stress distribution across the rigid head can be determined by considering the rotations of each of the chords of the stress field bounding the rigid field. So we will see that roughly in the upcoming slides. So the average pressure across the rigid head. So see, P by Cu, this is the pressure at this point. Okay, so let me just erase this. So this is the pressure at this point. Now just at the rigid head begins at this point, there is a discontinuity, right? So same point we have two pressures, it is increasing. So this increase in pressure is given by this term. Okay, 2 into twice I plus 0.5 d by twice x. Okay, and P is the pressure at here is this point, and then it is increasing. This increase is given by this term, complete term. So where P by Cu is equal to value derived from the stress field at the extreme end of the rigid head, as I said. P prime is the average stress over the rigid head. I is equal to summation of horizontal chord lengths into rotation, and x is equal to summation of horizontal chord lengths. D is equal to depth of soft soil there. Okay. For designing the geocell mattress, consider an element of soil within the geocell mattress, but interfacing with the soft soil layer. So geocell is there. So geocells, there are various cells. So in each cell, we are considering an element of soil inside the geocell. So geocell is filled with the soil, right? So whatever soil is filled in the geocell, in that soil we are considering an element of soil which is in interface with the soft soil layer. Okay, the horizontal stress on that element of soil is given by this equation, where sigma n is equal to vertical stress on the element and x is given by this expression. Now this x is a function of the phi. Here phi is the friction angle of whatever soil you are feeling inside the geocell. Okay, the granular soil, we will using a good quality granular soil to fill the geocell, right? So this phi prime is the friction angle of that soil, particular soil, which you are filling in the geocell matrix. Okay, that is the that phi. All right. Then we have t shear stress at the interface. So this is tau, actually this tau value. This tau is nothing but a shear stress at the interface. Cu in limiting condition. We will see that later. What is that? F is the friction angle for geocell material. This they are calling as F. Okay, this is phi prime. Okay, the rotation of principal stress occurs within the mattress step. Therefore, a geocell mattress having tensile strength equal to the expected horizontal stress might be used to support the embankment. So what does that mean? This means that you will calculate this horizontal stress, okay, on that element. We are going to calculate this. This Excel is really not Excel. This PowerPoint is really bad. Sometimes it behaves so abnormally. It's very frustrating. Yeah. So what I was saying, this you are going to calculate, that is the horizontal stress on the element. This you are going to calculate. Say you calculate this horizontal stress as 50 kilonewton per meter square. That means you have to use a geocell of thickness 1 meter. If your geocell thickness is say 1 meter, you have to use that geocell must have a tensile strength of at least 50 kilonewton per meters. Okay, this pressure is 50 kPa or 50 Newton per meter square. You need to use a geocell thickness 1 meter thickness having a tensile strength of minimum 50 kilonewton per meter. Okay, that is what this means. Okay, so whatever we saw now from slides 3 to 7 has been extracted from this paper by Professor Madhavi Leta, 2011, design of geosol reinforcement for supporting investment software geomechanics and engineering. So I suggest that you please go through this paper. Some design examples are also given in this paper. So if you read the paper very nicely, everything is clearly given, all the steps are given, one design example is also solved, so everything will be clear to you. So I suggest that you please go through this paper. Okay. Yeah, right. So now let us look into the problem that was actually discussed in the main class. Okay, just you will be having a casual glance over it. We just won't go into the depth because many things are not clear to me also. Okay, because I am also not in touch with this line method, so whatever they did I found a little bit confusing, so everything is not clear to me also. Still whatsoever we will try to just see what is done. So this was the question. Design an embankment resting on a thin layer of soft soil and supported by geocell mattress. So thin layer of soft soil, the soft soil is having a thickness of 4 meters. Okay, then we have a 6 meter high embankment over it, supported by geocell material. Height of the embankment is 6 meter and the thickness of the soft soil is 4 meter. Embankment has a slope of 1 vertical is to 2 horizontal. Okay, the top width of the embankment is 36 meters. Geocell mattress has a thickness of 1 meter. Okay, the geocell mattress that you are using, that geocell mattress is going to have a thickness of 1 meter. Embankment has a surcharge of 20 kPa and the unit weight of the fill is 18 kilonewton per meter cube. Okay, Newton per meter cube is the unit weight of the fill of the embankment. Okay, that is the unit weight of the embankment. So, undrained cohesive strength of the clay layer, means this layer, is 10 kPa. Okay, so all this information is given to us. Now let us see what they have done. Okay. Let us see what they have done. So this is the embankment. This is the embankment. So that you can see that they have drawn half of the embankment, right? As the embankment is symmetric, we have drawn half of the embankment. So 18 meters. So 18 meters. It is drawn, right? So then what they will, then we will provide some geocell layer like this. A geocell layer is provided, right? The thickness of the geocell layer is how much? Thickness of the geocell layer is 1 meter, that is given to us. Okay, that is 1 meter, that is given to us. Now this thickness is also given for the soft soil layer, that is 4 meters, right? 4 meters. Now what we are doing is that we are drawing some, as I said, at 15 degrees we are drawing some chord lines like this. Okay. At 15 degrees each we are drawing some chord lines. So you can see there is a family of curves. Steep lines are family of alpha lines and beta lines are there. Alpha lines and beta lines are there. Now from what is being done is that, so you have to draw this in a particular scale. So you first choose a scale and draw everything. Okay, well, let us see what them. From the above slip line field, G3H1 is an alpha line along which P plus 2I Cu is constant. So along any alpha line. So what are the alpha lines? So these are the alpha lines. Right? These are the alpha lines. Okay, these are the alpha lines. So along these alpha lines is P pressure plus 2I Cu. This angle is the what about the rotation angle. Okay, rotation angle that is constant. Now at G3, at this point, I will erase others. Wait. At this G3 point, we already know the what is the pressure. It is nothing but 5.71 Cu. We already discussed before. Till a distance d, it is 5.71 Cu. So here we know it is 5.71 Cu. Right, at this point we know it's 5.71 Cu. Now what we do, now the next step is to go along this line to find out the at this point G3H1. Along this G3H1 alpha line we go in order to find out this at H1 point. What is the pressure? So what is the pressure at H1 is nothing but pressure at G3 point plus 2I Cu is angle, the angle of rotation. So at PG3 is nothing but 5.71 Cu plus 2I Cu, this angle. So Cu plus 2I, what is the angle? Angle is nothing but 15 degrees. If you convert it to radians, it is nothing but 2.6. So one rotation is there, 15 degree rotation here. So we are having this 6.24 Cu. So this is the value at this point H1. Okay, so at H1 point we know this. Okay, H1 point is point we know this. Now we need to calculate the pressure at point H. So we actually have to calculate all these points at the base of the geocell what is the pressures. Okay, now we know at H1 point. Now again we have to go up to H point along the beta line. I need to go along the beta line. We need to go up. So to calculate the pressure at H along beta line, the rotation is plus 5 degrees. So this way you have to do. 2.62 return anti-clockwise along beta line. So beta is we get this is constant. So at H1 we have this. So P at this here at H will be nothing but PH twice U, same process we are following. So CL plus twice U will get this. Okay, so like this we are going to calculate it. Okay, so step by step. So if you know one point, you can just go along the alpha lines and beta lines, and you can go just continuously. If you know at one point, you can start from here, and then calculate the pressures at all the points, whatever point you need. Okay, at whatever point you need, you can calculate. Okay, at whatever point you need, you can calculate like this. Okay, one point you know the pressure, and then from there you can calculate the pressures or whatever stresses you want at all the points. This is the beauty of the slip line method. Likewise, similarly, we can get the pressures as all these points, and next what you have to find out, we need to find out at this point D, just beside the rigid head, we need to calculate. Okay, so the pressure diagram will be as well. Likewise, at the edge of the pressure head, this D is P33 plus 10 into 4. So 10, why 10? Because you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 number of jumps we are making, right? From here we are looking 10 number of jumps. So 10 and 4. I don't know why 4. I think they have done because of the height. So that, like that, they have calculated some chord length. So they have multiplied by 4. So finally they got it at the D, PD, they got this amount of stress. Now at D, I know it is the edge of the rigid head. I know the stress. Now I can find out the average stress along the rigid head. This is the average stress distribution along the rigid head, right? This stress distribution I can know nothing but 2 by 2 I say 0.50 by 2 I say. So they have done all the calculation here. You can see this table. Okay, this table, and finally we got this is got the stress here as 17.262 C. Okay, this is what we get. Now assuming 1 meter length of the embankment is out of plane direction, we are considering 1 meter length. So out of plane direction we are considering 1. It's a plane strain problem, so 1 meter length we are considering in the out of plane direction. Load from half of the embankment, because we are considering symmetric, so half of the embankment load it's calculated just by multiplying the unit weight and all those stuff, we will get this. Right. Now resistance from the pressure diagram is nothing but the area of this pressure diagram, nothing but the resistance of the soil using the with the geocell. So we calculated this and this. Now Cu, the required what Cu of the soil do you need to prevent plastic deformation is nothing but this by this, so you get 9.31 kPa. 9.31 kPa is the required Cu of the soil to prevent plastic deformation. Okay, this is the safe value of Cu. But our soil is 10 kPa. What is the Cu of our soil? The Cu of our soil is 10. Cu of our soil, the 10 divided by 9.31 is nothing but the factor of safety. So if the Cu of the soil is 9.31, just it is the limiting condition. That is, the soil is the limiting point, but the soil is not going to enter the plastic state. But our soil is 10, the Cu of our soil is 10. That means there is some factor of safety. So the factor of safety is nothing but this is not plus is equal to 1.07 for the marginally safe. But at least we need a factor of safety of 1.5. That means the soft soil should at least have a cohesion of 15 kPa, so that our factor of safety of the system is 1.5. Okay, that's the thing. Now horizontal. Now next step is to determine the horizontal stress within the geocell using this expression, as I said. So what is the vertical stress on the element is equal to gamma into height times surcharge, so 18 into 6 plus the surcharge 128 kPa. Now you have this expression. Now you put all the, so here so the interface there put Cu to this tau. This tau is nothing but the Cu limiting. So in the Cu limiting, actually here they have put an 8, so this won't be 8, huh? Here you have actually you have to put 9.31, this limiting condition. They have made some mistake here. So finally you put all the values and find out the horizontal pressure at this. You put the phi for the geocell material, whatever material you are filling in, all the stuff you fill, put, and then you find out the horizontal stress. So that means, so you are getting the horizontal stress coming into an element in the geocell. The horizontal stress coming into any element in the geocell as 52 kPa. That means a geocell of height having a tensile strength of more than 52 kN per meter has to be used. Okay, has to be used. The minimum strength of a geocell of height 1 meter, the tensile strength has to be 52 kN per meter. Okay. Okay. Now here some here I feel there is some wait. What, man? Here I feel there was so what I make some mistake. So what I suggest is that please go through the paper what I suggested here, okay, at the last, this paper. Please go through this paper, you will find some design example, so it will be very helpful to you. Clearly everything is solved there, so I suggest that you go through that design example once. Okay, you go through the design example once, so it will be very beneficial to you. Okay, so now since we have some time, what we will be doing is that we will be I thought that I will just discuss this extra topic with you. This topic is actually not included in your syllabus, since it is not discussed in the main class. But since we have lot of time today, almost 50 minutes, more than 50 minutes we have in today's session, so let just for your knowledge I thought that I will discuss this topic of unpaved roads. So hydroxyl reinforcement for unpaved roads. So what are unpaved roads? Okay, what are unpaved? So this topic won't be included in your syllabus. Okay, since it is not taught in the main class, but just as a information, just as a knowledge, you can you can go through this once. Okay, although this once only, just if you attend this session once, it will be enough for you. You don't have to like go through it again and again. Okay, so we have unpaved roads. So what are unpaved roads? Soft soil subgrades have sand or aggregates placed directly above it. So we have a soft soil subgrade. So we have a subgrade of soil. Okay, above the subgrade of soil, we directly put sand or stone aggregates. That means there is no bitumen layer or something like that placed. So that is nothing but the unpaved road. Permanent surfacing such as concrete or asphalt pavement is immediately not placed on the stone. Okay, not placed. So directly we have the subgrade, and over the subgrade we have the sand or stone aggregates that is placed. Road may be surfaced with quarry crusher run or chip seal for reasonable rideability. Means just crusher, you know, quarry crusher. Quarry crusher means the stone which you get from the river, hilly river basin. Okay, from that you take this to quarry, that is called the quarry, right? From there you take the stone, you crush it, you get some crusher run. So we just little small chips you get, you just put that over the aggregates. There is just a smooth, little bit smooth finish you will get, so that vehicles can move over it. Okay, then we have at a much later time, when the settlements have taken place and rats are backfilled, a permanent settlement may be placed or may not be placed. Okay, may be placed or may not be placed. So that is what we call unpaved roads. So initially, when the road is constructed uh, directly over the subgrade, we place the aggregates. Okay, that is the concept of unpaved roads. Now see, the Giraud and Noire actually use the geometric model that is shown here to define the concept of unpaved road. So you can see this H naught. This H naught is nothing but the thickness of the aggregate layer that you have to put over the subgrade when you do not use any geotextile reinforcement. Okay, when you do not use any geotextile reinforcement, you need to put a certain thickness of aggregates over the subgrade to make a unpaved road strong enough so that it can take the load of the wheels of the vehicle, right? So this H naught is the height of that aggregate layer that is placed. Now when we use geotextile, this height actually gets reduced to small h. Okay, that means with the use of geotextile we can reduce the height of the aggregate that needs to be used, reduce the thickness of the aggregates that is to be used from h naught to h. So the many kilometer long road, so if you uh, reduce the thickness of the aggregates, you can save a lot of costs, and it is more sustainable, right? Because lesser amount of aggregates you need to carry from somewhere and you need to place over the road, right? So it is more economical. Okay, so with the use of geotextile, what happens? The thickness of the the thickness of the uh, uh, the thickness of the aggregate that you need to use for the unpaved road, that you can reduce it. All right. So from H naught, the thickness reduces to H. Okay, from H naught the thickness reduces to H. So this at the top you can see PEC. The PEC, the length and L and B is given. So PEC, this PEC is nothing but the tire pressure, equivalent tire pressure. Okay, this equivalent tire pressure is actually distributed at some angle alpha. Alpha not in this case and alpha in case of when we use some geotextile reinforcement. So this is actually distributed in an angle alpha to the subgrade layer. Okay, to the subgrade layer. So it is distributed in an angle alpha and alpha naught and alpha in the subgrade layer. Generally this angle alpha naught is approximately 26 degrees, and this alpha is generally little bit more than that, I think, if I remember. But for practical purposes generally we consider it as same only, but actually this alpha and alpha naught is not same, it is a little bit different. But for calculation purposes and all, we can consider this alpha to be around 26 degrees. Okay, now this is alpha. Now other dimensions you can see, twice a naught, twice all these things are given. So please remember this, keep this diagram in your mind. So please keep this diagram in your mind, everything. Okay, please keep this diagram in your mind. Alpha naught, twice a naught, twice a, H naught, H. Okay, all this you keep in your mind. Okay, now this P naught, or this P naught is the pressure. It is pressure coming from the wheel load, distribution of the wheel load, and also the this thickness gamma into H naught. Or in this case when the geotextile is used, it is the PEC plus the gamma into H. Okay, gamma into H. So this P is the combined pressure that is acting due to the wheel load and due to the aggregates that we have put. Okay, aggregates that we have put, that is the combined pressure that is there. Okay, so now let us see next. Yeah. Just give me a minute. I will just drink a bit of water. Just give me 1 minute. Yeah, so I'm back. So what I was saying, yeah. So now see, from here you have this P naught, and here you have this P. So let me write this P naught and P for you. So this P naught and P, as I said, is the sum of the pressure coming from the wheel load, and then also from the weight of the aggregate that you have placed, right? Or that is the gamma into H or H naught. That is the weight of the aggregate that you have placed. Okay, where gamma is the unit weight of the aggregate. All right. So first, let me write P naught. So what is P naught? P is nothing but the wheel load, the load coming, total load, wheel load that is coming divided by twice beta plus twice H naught. Okay, plus gamma into H naught, F1. And then we have P, same, P by twice P plus twice H tan alpha by L plus twice H tan alpha plus gamma into H. 2. What is P? P is nothing but the axle load of the vehicle. Axle load, gamma, unit weight of the stone aggregate. Alright, unit weight of the stone aggregate. Right? Understood? Now this P, this we can have the pressure in case of when the soil is unreinforced. We can consider that the limit is the this is the limit of the soil, means this is the elastic limit of the soil. But when we use the what to say, this geotextile, when we use a geotextile reinforcement, at that time this elastic limit actually increases to this. Okay, elastic limit increases to this. So from pi c it will be pi plus 2c. Okay, so this you can equate to P naught, and this you can actually equate. We will see that how to do. Okay, so let me just mark this as 3, this is 4. Now from equation 1 and 3 we get, so in place of, in the left hand side, this P naught, so this 3 is nothing but P naught. Okay, P naught. So from equation 1 and 3, if in the LHS if you put pi c plus gamma into H naught, and RHS you have this P by, so from here you can get C is equal to okay. So from here we can substitute all the terms and get this H naught. Okay, we can get this. We will solve a problem that we will see. Now I will write all the terms for you, define all the terms. This is tire, Okay. Now for the case where geotextile reinforcement is used, equation 4 is equated to P minus PG. We'll see what PG is. Okay, so we have P minus PG is pi plus 2C plus gamma into H. Now what is this PG? Is PG is nothing but E. This is the elastic modulus of the reinforcement into strain elongation by A is the geometric property that we, if you remember from the figure, A root over 1 plus A by twice S whole square. Okay, so I will write E is the modulus of geotextile elongation metric property, and S is the settlement under wheel load. Okay, so these are the various parameters. So finally, if we equate all these things, we will get the second equation as plus 2C plus P plus 2H by plus 2H tan alpha minus E by A 1 plus A plus S square. So this is the equation from which you need to determine H. So one equation you got from where you will get H naught, and from this equation you are going to get H. Okay. Now these equations are were also simplified in terms of design charts. So Gerard and Norway actually gave certain design charts. So design charts like this. So you can see here for a particular wheel load, particular rutting depth, and particular tire inflation pressure, we have this set of curve or this set of curve. So from this curve also directly we can calculate the H naught, which is the initial depth where you do not use any geotextile reinforcement, and we can calculate the delta H. Delta H is the reduction in depth. Is H is equal to H naught minus delta H. H is equal to H naught minus delta H. Delta H is nothing but reduction of depth when we use a geotextile reinforcement. Okay, that we can directly get from this graph. Now, let us see this question. Let us see this question. Given 340 passes of 80 kilonewton single axle load vehicles with tire inflation pressure 480 kPa. So 340 passes happen in of 80 kilonewton single axle load vehicles with tire inflation pressure for 480 kPa. Soft soil CBR is 1, CU is 30 kPa, the modulus of geotextile is 90 kN per meter, and allowable rut depth is 0.3 meter. What is the required aggregate thickness of an unpaved road? First you need to calculate for the aggregate thickness for the unpaved road, means there is no geotextile reinforcement. Now see, what was the expression? What was the expression? C is equal to P by 2 pi root over P by PC plus 2 is not 10 alpha naught times root over P plus 2 PC plus 2 is not 10 alpha naught, right? This was the expression. So let us put all the values in that. So 30 is C is equal to 2 pi 80 axle load by pressure, axle pressure 480 plus 2 H naught 10 26, where 26 degree alpha naught we are considering, root over 80 by 2 into 480 plus twice h naught 10 26. Okay, so this is 80. Done. Right. Now easily how to calculate root over 80 by 480 is how much? It will be coming as 0.41. Root over 80 by 2 into 480 is how much? 0.29. 2 into 10 26 is nothing but 0.98. So we put all these values, we'll get 30 is equal to 80 by twice by 0.41 plus 0.98 each naught by 0.29 plus 0.98 each naught. Okay, so we'll get some quadratic expression. Plus 0.22 each naught plus 0.96 square is equal to 80. 0.9 plus so from here please find out find this out, find out h naught. H naught will be coming out as 0.31 meter. Now similarly what we have to do, we have to find out h. Okay, h. Now for h, in the expression of h, if you see, we have this a also, right? This a, so a also we need to express in terms of h. Okay, so first let us express this a in terms of h. So this a, I will write it here only. Okay, it will be better, where a, so twice a is b plus twice h tan alpha, and this can also be written as p by pc plus twice h tan alpha. So from here we can find out a. So a, nothing but half okay, this is a. So I can get now a is equal to what is p? 80 by 480. So we will get a as 0.21 plus 57h. Right, now next what you have to do, next you put everything in that expression, then pi plus 2c, right? C is 10 to the minus 3. In pascals I am writing, this is 80 into 10 to the power 3, 2.41 plus 0.98h, 0.29 plus 0.98h minus just put all the values, 0 a times 1 plus 0.21 square. So now find out h from here. Find out h. Do trial and error and find out h. Do trial and error and find out h, please. So this is a little bit difficult to solve like by hand, right? So what you can do, you can put some values in h, values of h, and you can see if you are getting the LHS side. Okay, like this. Try to use little trial and error and try if you see if you are getting try if you are getting h or not. Put some values of h and see if you are getting the left hand side, you are getting that will be the h value, nothing else, right? So just do something, do some trial, make some trials and check. Okay, so are you getting h or not? Are you able to get h? So h will come as approximately 0.15 meter. Therefore, what is the reduction of h that you are getting? 0.31 minus 0.15. So you can see 50% is reduced, right? Around 50% is reduced. Depth of height of aggregates or depth of aggregates you are able to reduce by the use of jet geotextile. Okay, so that is the benefit of using geotextile. Okay, now it is one more expression that is given by US Army Corps of Engineers modified CBR design method. So here you are using the values of the CBR. Okay, so here you are using the CBR values to determine the height, thickness. So h is given as 1 by 2. So all the terms, let me define the terms for you. This is h is in mm. H is aggregate thickness in mm. C is traffic in terms of coverage. P is equivalent single wheel load. Okay, equivalent single wheel load in Newton. Equivalent single wheel load, that is P. A is tire contact, not pressure, tire contact area. It is mm square. Tire contact area, how much contact the tire makes with the pavement or the road when during the contact. Okay, so this is the expression given by the US Army Corps of Engineers using the CBR value. And let us see. Calculate the required stone base thickness for an unpaved road carrying 5,000 covered edges of 45 kilonewton equivalent single wheel loads using a tire contact area of 300 mm into 450 mm for A stone on a kaolinite clay soil at 41% water content with a CBR1 with no geotextile reinforcement. The same conditions but with a geotextile whose data are typically of the table given below at 25 mm deflection. Okay, compare the resulting thickness. Okay, let us start. So first, for unreinforced, when there is no geotextile reinforcement used, at that time we need to find out. Okay, at that time we need to calculate. So H is 3.24 log of C. C is the traffic in terms of coverage. It is given as 5000 plus 2.21. Then we have P, equivalent single wheel load. It is given at 45 kilonewton. So in Newton it will be about 3 by 36 times the CBR minus A is the area, contact area. The contact area is 300 into 450 divided by 2030. Alright, so this is, so from here you can get 114.11 into. Okay, put A, your CBR is equal to 1. So it is given that for the same water content with the CBR 1 with no geotextile reinforcement unit, for CBR is equal to 1, this one if you calculate you will get as 488 mm. So this much thickness, so this much thickness of aggregate you have to put if there is no reinforcement. Okay, now let us see what we have to put if there if reinforcement is there. Okay, now from here just give me 1 second. I'm getting a Yeah, sorry for the interruption. I just got a call, important call actually. Yeah. So yeah, as I was saying that now we solved for the first part, right? When there is no geotextile reinforcement that is used. The second part is when we are using a geotextile reinforcement. Uh, so in that case, certain criteria is given, right? So we are given to 25 mm deflection is considered. So 25 mm deflection is considered and 41% water content. So from here we can get this value, right? 2.4. So what is this 2.4 value? Is 2.4 is nothing but the ratio of soil with geotextile by soil with geotextile, okay, without geotextile, okay. So that is CBR with geotextile by CBR without geotextile is nothing but 2.4. Okay, so now without geotextile it's given as 1, no geotextile is given as 1. So CBR with geotextile is nothing but 1 into 2.4 is 2.4. So now we have the CBR of the soil with geotextile is 2.4. So now directly we can put the CBR as 2.4 and calculate it. That's all. That is 302. So you can see a lot of reduction in depth is happening just by using a layer of geotextile. So it will be approximately 6 mm. So 38% reduction. Okay, 38% reduction is happening. Okay, so this was all about the geotextile when we use geotextile. But when we use geogrid, what happens is that, remember we use the pi plus 2 cu. Y plus 2 cu is the elastic limit when we are using geotextile, remember, right? Pi plus 2 cu. But in case of geogrid, what happens, it changes to pi plus 1 cu. That's the difference. Rest other all the things is going to be same. Okay, so directly from this charts actually we can find out the h naught as well as the reduction in height. So the new height. So you can see h naught is what? H naught is nothing but the height when no geogrid is used. And how to find out the high depth when geogrid is used? That can be find out like this. H is nothing but r times, you can see this r values given, right? So h is nothing but r into h naught, condition for r less than, small r less than, this rating depth less than 150 mm and no channelized traffic pattern, and h is equal to 0.9 times of h naught for r greater than equal to 150 mm with a channelized traffic pattern. Done. Okay, now let us see this question. A soil subgrade has a CBR of 1 and is to carry 1000 standard actual vehicle passes. So number of passes are given as 1000. Okay, with a maximum rutting depth of 75 mm. Small r is given as 75 mm. What is the required aggregate depth without geogrid? So let us find this out. When we do not use geogrid, what is the required depth? So our CBR is given as 1. So from here we can, so what are the number of passes? Number of passes, 1000 passes. So from here we can easily calculate for 1. And what is the rutting depth? Rutting depth is 75 mm. So here 1, then 75 means this number of passes is 1000. So here, so this value. So approximately you can take this as say h naught as 0.6. Okay, 0.6 approximately, I'm just saying, just for the understanding, approximately 0.60 meter. Now we need to calculate when this geogrid is used. When this geogrid is used, then what will be the reinforcement? So what is the geogrid type? BX1200 geogrid is given. So this is the graph for BX1200 geogrid. So come like this. So this is the graph for BX1, this one. 1 to, and what, so we are getting a R of approximately here, right? So 0.55. So 0.55 R we are getting approximately R is zero point 0.5 or 0.55. So we are getting R is equal to 0.55. So therefore H is nothing but, now your arcing depth is less than 150 mm, it is 75. Now so it is R into H naught, since R is less than 150 mm. Okay, so it is nothing but 0.55 times 0.60, whatever you come, you write it down. Point it will be point how much, 0.55 times 0.6, 0.33 is 0.33 meters. So initially without the geogrid it was zero point 0.6, now it is reduced to, the depth of aggregate required is reduced to 0.33. Alright, now you must be wondering what is BX1200 geogrid. So for your information, I have given you here from the Tensar. BX1200 geogrid is a product of Tensar. Tensar is a company, they manufacture all this stuff. So all the properties of BX1200 geogrid is actually given here. So you can see the aperture dimension, minimum rib thickness, tensile strength, okay, tensile strength, the 5% ultimate tensile strength, junction efficiency, aperture durability, all those things are given to you. Okay, so this was so all for today's session. I hope that everything was clear to you, and if you have any doubt, please feel free to contact me anytime, write me over the email or anything, whatever, it's your choice, please contact me anytime. And today's session was a little bit simple. We discussed everything, and this part, whatever we discussed now regarding the unpaved road, that is the extra part, that is not a part of your syllabus, but just as we had time, I thought I will just give you some extra knowledge which will be beneficial for you in the future. Okay, so next class, our next class will be on the 15th of September 2024, that is next Sunday. The coming Sunday, today is one Sunday, the next Sunday 15th of September, so Sunday, from 3 p.m. to 5 p.m. our usual timing. On the next Sunday next week we'll be having that on the 15th of September. Today is 8th, and the next week, it is on the 15th, we will be having the one more class. We'll be discussing the 8th week session with the 8th week classes. Okay, so almost we have covered up the more than half of the journey of this course. So total we will be having 8th, 9th, 10th, 11th, 12th, 8th, 9th, 10th, 5 more 2-hour sessions, and last at the end we will be having one more 1 hour session. Okay, just 1 hour session we will be having at the end probably. So 13th session. So with this we will end today's session, and if you have any doubt, please feel free to contact me anytime, and see you on the 15th of September Sunday from 3 p.m. to 5 p.m. And as we have time now, 5-10 minutes, 5 minutes around we have, so I will be here. So if you have any doubt, you can just ask me anytime. Okay, so I am here, but our class is over for today. Okay, I am here till 5 p.m. Okay, so if you have any doubt, please feel free to write over the chat or ask me. All right.